MDM4U 8.4, normal approximation to the binomial distribution. So we have covered the binomial distribution in the past, and we've just recently learned about a continuous probability distribution, the normal distribution, a common continuous probability distribution in which the data are distributed symmetrically and unimodally about the mean. So this is the standard model used to be able to approximate areas underneath the curve, which gives us the probability of a certain outcome. So different values of the random variable x. The binomial distribution is given by the following formula, and a distribution having independent trials whose outcomes are either success or failure, the probability of success is unchanged from one trial to the next, so independent trials, and the random variable is the number of successes in a given number of trials. So really the input values are how many trials are there and the success, because Q is calculated as 1 minus P. So really there's two variables that are needed to understand a binomial distribution. That being said, the expected value of a binomial random variable is given by this formula. The expected value of x is equal to n times p, the number of trials times p, the probability of success. And that'll tell you what the average outcome is from an experiment with n trials. When can we use a standard normal curve to approximate a binomial distribution? Remember, a binomial distribution is discrete, meaning that we have bars representing specific separate outcomes. And a continuous curve is a smooth curve. So let's investigate a couple of these cases by adjusting the following variables, n, p, and see how that affects our curve. So n is 10 and p is 0.5, and we have a symmetrical and unimodal, meaning one peak, curve. And that kind of matches our smooth curve. And what we're going to be investigating is why is it that np must be greater than 5 and nq must be greater than 5 in order to use the continuous normal curve to approximate probability or area underneath the curve of a discrete variable, the distribution of a discrete variable. So in this case, we're measuring n times p and n times q. And notice this right here. When np is dipping below 5, this is less symmetrical than the previous, and therefore normal curve would be less suitable to approximate the probability, less accurate. And even worse here, same number of trials, 10 in this first row. And lastly here, it's close, but it's not really symmetrical. So you're losing accuracy when you're using a continuous model to approximate each of these. Now notice when NP and NQ were highest with our first example, that's when it was best. And notice 6 and 4 is not so bad, but there has to be a cutoff at some point, and this is just chosen at some value. It had to be some rule of thumb. Next, in each of these examples, E through H, the number of trials is 100. So you notice that the bars are a lot slimmer because there's more outcomes that are possible. We are looking at the different probabilities. That's the only variable being adjusted, and let's take a look at the outcome. So at p is equal to 0.5, 50-50, we have what appears to be almost a perfect unimodal symmetrical curve or distribution. Similarly, this right here is a symmetrical unimodal distribution, but notice that it's shifted from the middle 50 over to the left around its expected value. NP is equal to 25, so that's the mean of this distribution. And a normal curve would be suitable for this right here. Both are above 5. In this case here, even though it's really skinny, it's still symmetrical and unimodal. And we refer to that stretch upwards or the width of a distribution as the kurtosis. So the kurtosis in this case would be skinny. This right here is wide. And then lastly, when we have 100 trials, these were all suitable, but looking at this right here, if the probability of success is only 1, we expect to have 1 out of 100 in a trial with 100, in an experiment with 100 trials, and that's not really suitable to approximate with a normal curve. So that's the justification for why we must have NP and NQ greater than 5. It just makes for a symmetrical unimodal binomial distribution. So the mean can be approximated with that expected value, NP, and the standard deviation for a binomial random variable can be approximated using sigma is equal to the square root of NPQ. So this is a new formula that we'll be using in the circumstance that we have a binomial random variable and we want to know what we would expect to see for the standard deviation. So because we are using a discrete random variable, we should make a continuity correction when we're using a continuous curve to approximate probabilities. Next, what we're doing here, it's out of frame. I'm just going to adjust one feature. Better. So, a bank found that 24% of its loans to new small businesses become delinquent. If 200 small businesses are selected randomly from the bank's files, what is the probability that at least 60 of them are delinquent? Compare the results from the normal approximation with the results from the calculations using the binomial distribution. So let's start off with the normal approximation. The normal approximation means the following. So we're going to use that normal curve in order to approximate the probability of 60 or more. Because of all of the possible outcomes, we could have 0 all the way up to 200 of the businesses becoming delinquent in a sample of 200. So it's not very likely to have some of those outcomes, but they're all still measurable, and a continuous curve can help us measure those probabilities. So N, P, and Q are the following values. We substitute into NP and NQ to determine if it is an appropriate approximation using a continuous curve for this for this discrete data. So we use mu is equal to NP and sigma is equal to the square root of NPQ to get our statistics for the sample. And we were interested in the probability that x is greater than or equal to 60. So what we will do is, first of all, continuity correction. This we want to include 60. So we'll go to the left endpoint of that outcome, the bar, and measure the area above. And because this is probability greater than a particular value, we'll do 1 minus the indirect method to get the part that we wish to exclude. And since our z-score table measures areas to the left-hand side, we will make the approximation of this calculation using the z-score formula, the deviation, which is x minus mu divided by the standard deviation. That gives us a z-score of 1.90, which we look up on our table, and that's equal to approximately 0.9713. And this is our result. 1 minus our probability of being less than this value is equal to 0.0287. Now, what I've used is a binomial distribution calculator online, and all that you need to input is the number of trials and the probability of success, and that will tell you, first of all, it'll show you what the distribution looks like. Notice that this could have, for the random variable x, anywhere from 0 to 200. It's zoomed in on where the outcomes are actually somewhat likely. Notice that even the most likely outcome, because there's so many different outcomes, it has to be shared among them, is a very small slice. The most likely outcome is approximately 7%. That being said, if we were looking at the probability that x is greater than or equal to 60, we can make that selection here and it'll calculate the value for us. But what I'd like to do is practice some of our skills with Microsoft Excel and doing this calculation. So if there is the following, I've just written the random variable x, probability of x, and then this information here just for me to be able to recall on exactly what it is we're talking about. So the details of our binomial distribution. We're looking for the probability that x is greater than or equal to 60. So what we're going to do is come up with all of the possible values of our random variable. Remember the autofill feature, where if there's a pattern started, we can scroll down, and this is going just out of frame, but a box in the right corner is telling me where I'm at, and I'm going to go all the way up to, there it is, 200. Because there's potentially 200 different 200 outcomes. That being said, 0 to 200. I think that's 201. Next, for our probability formula, all we're doing is substituting in our values for the binomial distribution formula. Combination is a built-in feature, and it's just asking for the number that we wish to use. There's 200 total. That will never change. So I'm going to use that number, use a comma. That's looking for the next input is the number chosen. We're going to choose 0 for the first case, and we're going to multiply using the asterisk in computer language, multiplied by the value p to the number of successes. So 0.24 will always be the probability of success, and that'll be raised to the power 0 in this case, or the value of x that we're interested in this circumstance. And then we can use the complement of, that'd be 0.76, or just 1 minus 0.24 to the power. This is going to be the total, 200 minus whatever your random variable x is. And that's just the binomial formula. And we're going to end up with this right here, which is it's a power notation. That e represents times 10 to the power negative 24. So we move the decimal place over 24 units to the left. So it's not even really a significant result. As we saw with our distribution graph, most of the results were around that expected value. NP was equal to 48. So we start to see values that are reasonable in this area here. If we were to want to see that ourselves, we could select both of these here, insert, look at the recommended charts, and we'll see that distribution here. We can create our own graph as we so choose. That being said, we are looking for the probability that x is greater than or equal to 60. So that's from this point onward. And we can accomplish that by looking at our random variable here. I just wanted to have, this is going to be probability that x is greater than or equal to 60. And this is not going to convert it to that greater than or equals to symbol, but that's what that looks like, greater than equals to. And this is going to be our value. So 60, what we're going to do is take the sum. We're going to add up those cases that we wish. Or I can be clever and use the indirect method. I'll just look at the first 59 cases, because greater than or equal to 60, I can either go from 60 all the way up to 200, or I can look at it from 1 minus 0 to 59, those cases, minus the sum of these cases. And that'll just mean I'm highlighting less cases, which is convenient. All the way up to 59. Those are the cases I wish to exclude. I didn't close the bracket. So notice this. Let's see how close this is to our binomial distribution calculator. Precisely that value. So just wanted to practice some different skills. The approximation using the normal curve was off by only, let's see here. Let's get back to our document really quick. Not the one. Not by much, 20287, off by very little. So it was a pretty good approximation for what we were looking to calculate. Okay, good luck with the homework questions.